Hello, my name is Stepan Nassyr. I'm a PhD student in the Jülich Supercomputing Center within the Application-Oriented Technology Development Group led by Professor Dirk Pleiter. This is an extended version of the talk I've made for BLIS Retreat 2020, held on October 5th earlier this year. I am investigating future Arm-based architectures for supercomputers, and thus one of the foci of my work at the JSC is the new Arm Scalable Vector Extension, SVE. It is essentially the successor to Neon, which used fixed 128-bit vector registers. You might also be familiar with similar extensions for other platforms, for example AVX2 and AVX512 on x86, which use fixed 256-bit and 512-bit vector registers respectively. SVE takes a different approach. Here the vector size is not known to the programmer. It is still fixed in hardware, unless of course the processor has special functionality that allows reconfiguration. And it is constrained to multiples of 128 bits, up to a maximum size of 2048. And while SVE does not necessarily call for larger SIMD registers than Neon, it is reasonable to assume that the first implementations will offer power of two sizes similar to AVX2 and AVX512. For example, the newly conquered first place in the top 500 is held by RIKEN's Fugaku system, which is based on Fujitsu's A64FX processor that uses two 512-bit SVE units. Since the vector length is not fixed, SVE allows for vector length agnostic programming, compiling code once and running it on any SVE-capable processor. Of course, this does not guarantee optimization. BLIS is a software framework for instantiating BLAS-like dense linear algebra libraries. One of the advantages of this framework is its ability to enable most of its commonly used operations by just implementing a few optimized microkernels. SVE offers many tools to accomplish vector length agnosticism: predicates that can mask elements, instructions to generate those, and tools for loop control without having special cases for less than vector width remainders. However, for BLIS kernels, we do not need those. We just determine the kernel size at runtime and dynamically calculate the block sizes during context initialization. Multiple companies that currently offer Arm-based HPC systems will offer SVE-capable products in the future. The predecessors of these systems support Neon. Some of the cores that are available to us for testing are Arm Neoverse N1, Marvell ThunderX2, and Huawei Qinpeng 920. We use Neon to test our general approach on these systems. We have written multiple VLA and non-VLA gem kernels, with the main focus currently being dgem. Using the Gem 5 simulator and SVE-capable hardware, we are investigating the performance of these kernels on those simulated and real cores. For non-VLA kernels, we treat SVE just as any other SIMD extension. We assume a fixed vector size, which can be specified at compile time. As for the VLA kernels, one dimension is fixed, and the other is n times the SIMD width. The exact size is determined at runtime. In investigating kernel performance, we implement different kernel sizes and different ways to structure the kernel, using different layouts and instructions. To facilitate creating kernel variations, we applied a modular approach, using macros for commonly used code blocks. Our Neon kernels use a similar approach. Here we only have fixed size kernels and verify our block size calculation. There are four parts the kernel consists of: initialization, which includes loading addresses and initial values into registers, any additional setup, as well as initial memory prefetching. The main K loop, in which the A times B matrix multiplication is performed. Code that handles the remainder. And finally, the finalization that loads the CR tile, scales C with beta and A times B product with alpha, and saves the tile back to memory. Let's take a closer look at the initialization and main loop of one of the kernels and see how some of those macros are used. The initialization can include machine-specific optimizations. Here a macro is utilized to make use of A64FX's sector cache feature, tagging addresses with some high bits that indicate which cache sector to use. The feature is controlled by a definition at compile time. If it isn't enabled, this macro does nothing. Here some initial prefetching is performed. The pref256 macro will only perform a prefetch if the cache line size is 256 bytes. Here is the main loop of the kernel. This part tends to be very verbose and error-prone, so we abstracted it away in 4 blocks. In this kernel, which has the dimensions 2 vectors times 10, there is an issue with the number of available named vector registers. We require 10 to save values of BR, but only 8 are available. We rotate them to keep the dependencies as many instructions apart from each other as possible and hide latency. Specifying the registers as parameters to a block macro reduces the risk of making a mistake. This isn't exactly mind-blowing computer science, but many microkernels use verbose inner loops and they tend to be difficult to debug. Apart from register names and offsets, the macro also takes a prefetch mode parameter. You'll see what this does in a bit. Let's take a look at what is inside one of those blocks. You will see macros for loading vectors, and to perform SIMD multiply accumulate operations on multiple rows. These macros, by the way, expand to some SVE instructions that are not shown here. There is also the prefetching, and in this simple case there is only pref and no pref prefetch modes. Either prefetching or not prefetching a 256 byte cache line 4 kibibyte into the A matrix. And although not shown in this video, macros are also used in the other 2 parts of the kernel. As previously mentioned, we are calculating the block sizes at runtime, using the method described in the analytical modeling paper by Zemeng Law et al. Here's how we do it. First, get the vector register size using an SVE instruction. Then calculate the kernel size, i.e. block sizes MR and NR. Adjust them to the size of the kernel closest to these calculated values. The kernel gets chosen later, according to these adjusted numbers. Then we calculate the rest of the block sizes and, of course, initialize them. As you can see here, we have so far only worked on single, double, and complex double versions. We added 2 compile time parameters. The SVE vector size, which can be either VLA to use vector length agnostic kernels, or a valid SVE bit size. And whether to allow the special complex arithmetic instructions available in SVE, which can be used by the complex kernels such as ZGEM. We have the switch to investigate potential benefits or drawbacks in using those instructions. We currently control other compile time features by adding defines to C flags, like the cache line size for prefetching or machine-specific optimizations. We have not yet finalized how this is going to be exposed, if at all. For example, a more BLIS-like approach would be to define an A64FX platform, which enables specific optimizations. All this will likely change before we attempt to add our work to mainline BLIS. We have also realized that it is beneficial to be able to override architectural parameters at runtime, especially when working with simulated cores where the configuration can be changed. For example, in Gem 5, important architectural parameters can be easily configured, like the cache line size, associativity, latency, etc. There are also ways to configure instruction latencies and other aspects of the simulated architecture. We added 2 debug features that help in tuning and verifying our code. One is the ability to override block sizes with environment variables. This is useful to verify the automatic block size calculation and might also be a useful feature overall, because the performance for different problem sizes can depend on the block size you choose. The other feature is the microkernel override. We have implemented multiple kernels and have already observed that the preferred kernel differs from one platform to another. Here, to give an example, here's a run of the benchmark that is included with BLIS. And here the block sizes and kernel are overridden, as well as some other BLIS environment variables relating to multithreading. If you have access to an A64FX system, try configuring the benchmark test DGEM with larger matrices, say something above 10,000 times 10,000, and run this exact command. Also, you should build BLIS with this additional prefetch 256C flag. Here are some performance numbers. For simulated cores, the performance looks pretty good, reaching over 90% efficiency for larger problem sizes. Our Neon numbers also look promising on the Arm Neo version 1 dev board, where we also see over 90% of the theoretical peak. We only recently got our hands on some Quinpong 920 nodes, so we couldn't add any specific optimizations, but using the kernels we added for Neoverse and our block size algorithm, we also see very good performance. As for the performance on real SVE hardware, we have to ask you to stay tuned. Our target for publishing our A64FX results is end of this month. If you are interested in our work, you should take a look at our public repository for BLIS. Be sure to select the SVE release branch and read the README SVE file for more information. To summarize, we have implemented double, single and complex double SVE gem microkernels, as well as added more dgem neon kernels for Neo version 1. Our SVE port is vector length agnostic by virtue of selecting the kernel and block sizes at runtime. We also added debug features to override microkernel and block sizes with environmental variables, which helps with tuning and verification. And our performance results on Neon and SVE hardware as well as simulated cores looks promising so far. Thank you for your attention.